Hi everyone, this is Gan, a researcher at MIT and IBM. I'm very excited to share our team's effort on building a world simulator, ThreeDWorld, for embodied intelligence. A long-standing goal of research in AI is to engineer machine agents that can interact with the world. Such AI systems must learn to perceive and understanding the physical world around them in order to be able to manipulate objects and formulate a plan to execute the task. Because direct training model with real robots is expensive and involves some safety risk, there has been a growing interest in using 3D simulator to build and benchmark embodied AI and robot learning models. Here I list a few representative 3D simulator, including iGibson, Habitat, iTuSol, Virtual Home, as well as Sapien. We also joined this effort to building a general purpose world simulator named as ThreeDWorld, or in short, ThW. This platform was born as an internal tool 4 years ago, and the initial idea was by generating scene in a virtual world, we could have complete control over data generation with full access to all associated generative parameters. This would enable us to train much powerful machine perception system. And since last year, we make a strong push to open source this platform and also switch its main focus from passive machine perception to embodied intelligence, robot learning, as well as cognitive-inspired AI. To begin with, I would like to give a brief introduction about ThW. So ThW is a multimodal platform for interactive physical simulation, building on the state-of-the-art game developer platform Unity. Unity handles image rendering and physical simulation for us and allows for a very diverse set of use cases. Here, I summarize 3 key aspects of ThW compared to other simulators. First, it's highly flexible and generally designed. So ThW was designed to accommodate a range of key applications in AI, including multimodal perception, physical scene understanding, robot learning, and with the goal that can enable training in each of these domains using a single simulator. Secondly, it supports multimodal simulation, which allows us to create a synthetic image dataset at near photorealistic level and generating sound at a high level of acoustic fidelity. And the most importantly is that ThW has advanced physical simulation abilities. It allows rigid body objects, soft body objects, clothes, and fluids to interact with. So there are multiple ways that we can interact with objects and generate physical realistic behaviors using ThW. Users can affect objects directly through API command or indirectly through embodied agent. Users can even interact correctly in VR, picking up virtual objects using virtual representation of their own hands. And this platform also opens up a new opportunity for us to redefine a new embodied AI task in both photo and physical realistic virtual environment. So in early this year, we released the ThW Transport Challenging, a visual guided task motion planning benchmark for physics to advance the physical release embodied AI. And we are also very excited to host this challenges at the CVPR Embodied AI workshop. And the motivation behind this dataset and challenging is that we find most of the tasks defined in currently virtual environments mostly focus on visual navigation, but pay little and no attention to the physical interaction. Since the ending goal of embodied AI is to building systems that can perceive and interact in a physical environment, physical interaction is clearly a necessary component for training home assistant robots. And concurrent to our work, several well-known researchers from computer vision and robotic communities also propose using rearrangement of objects as a potential testbed for embodied AI. So our dataset provided an example rearrangement task and with a clear evaluation metric and task definition that can be used to test embodied agent task and motion planning abilities in a photo and a physical realistic environment. So in this new embodied AI challenges, a robot agent is required to take action to move and change the state of a large number of objects to complete a complex goal in a photo and physical realistic virtual environment. Concretely, an embodied agent is randomly put in a simulated physical home environment, and it must collect a small number of objects scattered around the house and transport them to a specific location. In this example, that they need to transport ball and jug to the bag. The objective of this task is to transport as many objects as possible, given a limit interaction budget. We also position several containers around the house that can be used as a tool to transport objects efficiently. So without using container as a tool, the agent can only transport up to 2 objects at one time. However, while the container can help agent transport objects more efficiently, it will also use up some of the valuable interaction budget to fund this kind of container. So therefore, the agent must reason about a case-by-case optimal plan. And we created a ThreeDWorld house data to support this challenge. As shown in this figure, its home environment contains around 6 to 8 rooms, and the example including a bedroom, living room, and kitchen. And this room are then fully populated with furniture and objects that all respond to the physics. And in this challenge, we using microbot as the embodied agent. We also implement several high-level physics-driven action API to enable the robot to interact with objects. So the researcher can using commands such as go to grasp, put into container to train their robot to interact with the object and complete the task. And the observation space in the challenge contains a first-person view, RGB images, and a depth map, as well as the semantic segmentation mask. The agent could using this observation to estimate output map, and it can also obtain the object list based on the semantic segmentation mask. And we believe this long horizon task in the physical realistic environment pose several unique challenges for embodied agents that go beyond the traditional semantic operation. So the new challenge including the synergy between navigation and interaction. So the agent cannot move to a graspable object if this object is not in the egocentric view, or if the direct task is obstructed, for example, is occluded by a table, in the example. Second, the physical aware interaction. So grasping might fail if the agent's arm cannot reach the object. And third is about physical aware navigation. Collision with obstacle might cause object to be dropped and significantly makes the transport inefficiently. And last and most importantly, we really care about the reasonability of robot, and we design some two use case and and hope the robot can have some common sense to succeed in this task. Here show example about how the data set look like. A robot agent is required to find a small number of objects that scattered around the house, pick them up and transport them to a desired final location. And again, to complete the task, the robot agent must plan a sequence of options to change the state of many objects in face of this kind of release physical constraint. So we truly believe that this work simulator as well as benchmark will take a meaningful step that to empower research to develop a more human-like intelligent physics-driven robot for the physical world. And again, I would like to thank all the collaborators from MIT, IBM, Stanford, and please also check our project webpage for more detail and also the recent update.